you'll see it before it goes anywhere. But
yeah,
here we go. This is our maiden voyage, possibly last voyage. It's recording.
I hope not. I hope it's not the Titanic.
Yeah. So just for the sake of completeness, I'm Vineet Tiruvadi. I'm an MD PhD at Emory and GeorgiaTech.
And I'm Bilal Bari, MD PhD at Johns Hopkins.
And both of us are coming in with a deep background in engineering, about to embark on residency applications, about to embark on residency decisions, life decisions. And we've, I don't know, you and I have been talking gradually over the course of like 6-7 years. And it's interesting to see a convergence now of engineering in medicine in the context of everything that's happening. The research in medicine. So we figured we'd record this and just have our usual chat and see if anything useful comes out of it.
Well, I hope so.
Sorry, so you were saying?
Yeah, well, so the question of mixing how does engineering play into what medicine is? Yeah. And so I think in order to kind of get at that, for me at least, it's useful to think about what engineering is to you.
Yeah.
And so I think engineering as it's traditionally defined is problem solving. Which to me is quite vague, and potentially vague enough to the point of not being that useful. And so I like to kind of think about engineering, maybe also, I find that it helps to define things in terms of how they contrast to other fields.
Yeah.
And so especially, being in medicine where it's so biology focused, then, the parts where engineering kind of contrasts to biology, one of the first things that comes to mind is in engineering, one of the first things you learn is you lay bare your assumptions.
Yes.
Right? You say straight out, assuming blah. There's jokes about it, assuming the heart is a cylinder or a sphere, assuming a horse is a cylinder.
Yeah.
But I find that it's quite different from biology, and I'm intentionally casting a wide net here. I'm generalizing. I don't mean to speak to all biologists. But I have this sense that if you go and you give a talk for a biological audience and you say, assuming whatever, I'm going to lay out this problem, there's almost a hush that goes through the crowd, which is like, oh my God, he just made an assumption. Right? And then
you know what they say about assumptions.
Yeah, exactly. Right. And it's just one of these things where I don't think it's explicitly said, but I feel it, right? You feel the sense of people saying, oh, is this really a scientist? Is this really a person you can take seriously? So which I find a bit odd.
Yeah.
Personally, right? Because it's more of a cultural thing. It's not that biology, you don't make assumptions. I feel in biology, oftentimes you don't state the assumptions. And I don't know if you had any particular thoughts about that.
I think one of the most surprising things about the interaction with engineering and medicine is so much that we can go years without necessarily talking about the same subject, and when we come back, we're using the same language. We're talking about things in the same way. We frame assumptions. We frame the problem-solving process in the same way. I agree with everything you said. I think medicine and biology have this potentially bad but understandably necessary habit of, let's assume our measurements did reflect what we thought they reflected, but let's not say that. Like we will proceed kind of pushing the assumptions aside. It's a very much a polite thing to not state your assumptions, and then talk about your methods and talk about your results in a very fixed frame. I would agree. I think the assumptions are very much there. They're just embedded in the citations. They're embedded in this hazier information in who you choose to cite, who you don't choose to cite, how you frame your introduction, how you frame the motivation of isolating these particular two variables. There are assumptions all over there, but there's not an explicit addressing of why did you choose those two variables in the context of why did you not choose these 50 other variables? I don't know if that addressed your question, but yeah. I think that.
I also wonder if, I think just given the competitiveness that exists in science, if right, because to some extent, to state an assumption is to state a limitation, is to state a weakness.
Yeah.
Right, at least in neuroscience, for example, at least the kind of mouse circuit physiology work that I did and the field that I was in for my PhD. People might use a technique, I don't know how familiar you are, two-photon calcium imaging to report some measure of neuronal activity. And if you're in the field long enough, you understand the limitations of that technique. Limitations being, it's not really quite clear what the mapping between the calcium signal and spikes are.
Yeah.
It's a tool that can pick up, it's got good dynamic range for positive changes in spiking, but not negative changes. So you can't really see inhibition that well. And so, but what's interesting is if you kind of mention those weaknesses, and again, I think this is probably due to just the ultra competitive nature of science nowadays.
Yeah.
Is there's a need to defend and say, oh no, these aren't really as weak as you think they are. Right, and oftentimes it's pointing to an absence of evidence, saying, well, we don't really know.
Yeah.
Therefore, we don't have a reason to suspect that things are weak. And so all of that together, I think it's kind of a unique perspective that the engineering training has given me, which is that, you know, as much as you might try to hide it, I do think it enriches your thought and it enriches your ability to kind of, you know, frame a question well, if you're aware of, you know, what limitations you're putting into being able to frame that question, what assumptions you're using. And so that to me is at least one difference that I felt both in medical training and during the PhD that I thought that something that the engineering background gave me.
Yeah.
That I wasn't quite sure I saw elsewhere.
In a similar vein, and I feel like I was just having this conversation with more physician types, where a lot of it is this there has been a change in the objective function of science. So clearly I'm already coming in with a little bit of the control theory background that I really
please.
But it fits into this conversation, I think, very well. Engineering is not so much about individual hypotheses. It's about how you achieve hypotheses, how you test hypotheses. It's the process by which you get to where you want to go. And maybe the one thing we share in common is not so much our destination or our vehicle, but the nature of deciding our destination, the nature of deciding our vehicle, how we think about setting up the problem. And this has been in the same way of clearly outlining your assumptions. Draw your system diagram. It's wrong. It's wrong. Get over it. It's wrong. But if you write it down, you don't feel overwhelmed when you figure out that it's wrong. You come in, you put in a new piece, and you say, I think it's related this way. It's an empowering transparency that I think engineering brings, that medicine hasn't always been transparent. It has been this intuitive, maybe more art than science. I don't know what that art versus science thing means, but that's a whole topic for another day. But I think you said it well. If you lay out the assumptions in a hyper-competitive environment, in an environment where the objective is to maximize something, maximize production, those honest, transparent depictions of limitations and assumptions become weak points in a theory. They become easy weak points in a theory. They become easy avenues of attack to say, that's why your particular hypothesis, which you've staked your career on, because to test your hypothesis, you need to control n-2 variables. That's expensive. That requires a lot of ancillary funding. And so over the course of 10 years, you learn the techniques, specific techniques to control n-2 variables. And at the end of it, you find, that's not a significant result. But you've learned such narrow tools to isolate n-2 variables that you don't know how to shuffle it. And instead of studying A and B, how do you study B and C? Well, that's actually first of all, someone else did a PhD 10 years in that. So they're the ones that are going to get the funding. They're the ones that'll get the postdoc position. So it's best to not maybe put your assumptions. Maybe that's a cynical view. I think that might be a cynical view. I will say that, but there are the kind of openness to assumptions comes from the shared goal. Let's say I'm not interested. I'm not considering myself an expert in combustion engines when I want to build a car or a motorcycle. I want to get somewhere, and I want to get there in a fun way. So if a new engine type comes up or a new engine piece comes up, I'm thinking not, how do I defend myself against this? This engine type that I've been working with, how do I make sure that it is the one that wins this battle that doesn't even exist? Instead, I think, how do I incorporate that into this to improve it? And everyone's kind of building on that to try to get to the cool goal of I want to get there maybe, or I want to get there, or I want to get there the funnest way.
Yeah.
In that kind of, I think, sets the stage of where assumptions and systems diagrams come in, but then the medicine component of it. That I'm very curious about how your experiences in the first 2 years of medical school specifically were maybe enriched, maybe made more difficult by engineering, and then obviously third year, fourth year as well. But we're still in the middle of it in a unique time. So
yeah, I definitely think first 2 years, it's definitely, it's different, because one of the things when I reflect back to my time at Georgia Tech is what made it so difficult is how conceptually driven the entire curriculum was.
Yeah.
Right. It's like just finishing homework wasn't enough, for example, to feel like I really understood that chapter.
Yeah.
Right. And it required like really delving in and saying, okay, well, what are these equations really telling me?
Yeah.
Because, right, even if the objective is just to get a good grade, you can't memorize your way there. Right. You have to know how to take equations, do, kind of the whatever it takes to really wrap your head around it and make sense and say, what is this actually telling me that I might not have learned rote, but it's quite clear looking at these equations that I'm able to do X, Y, and Z.
Yeah.
And so I think what was difficult is going into medicine and recognizing, at least with the first 2 years, is that out of necessity, and I do think it's out of necessity, is that has to go out of the window. Right? When you join the ranks of medical school to become a doctor, you need to learn a new language, and you need to learn it quick.
Yeah.
And the way to do that is combination of memorization and kind of the enrichment that comes from living in that environment. Yeah. And so for me, I wasn't quite sure if the engineering, maybe you feel different about this, but I wasn't quite sure if it necessarily helped. To me, it felt like a completely orthogonal dimension of my life. The part of me that really, the part of me that quite frankly helped me in research, which is let's try to take noisy, messy data and in this brain try to reduce its dimensions and conceptualize it. That way of thinking didn't really help in medicine, where you have to know everything. You have to know every exception. You have to know, side effects. You have to know, the associations between different conditions, so on and so on. Yeah. So yeah, I don't know. I feel like early on in training felt like a limitation. Not a limitation. It felt like it hadn't necessarily helped.
Right. Right. I feel similarly. I think I was a little bit more reluctant than you to change my perspective on that. So the best example I always go to is machine learning and regression fitting, for example. We were being, medicine is a living field. It's constantly changing. The information that they're giving and they're testing will change in a year. Mm-hmm. So part of me, and keep in mind this was 7 years ago and my attitude has matured. 8 years ago, I thought to myself, and I paid dearly for it, but I said, let me find the common theme here. Let me find the underlying principles here. And I will do the tests based off of those underlying principles. There aren't many underlying principles that we know of yet in medicine. So naturally that was reflected in missing the questions that were a little bit more specific about things, but it was definitely a struggle. orthogonal would be putting it nicely. I think they are opposite. I think one type really stresses the thought process of, I will never forget my physics classes, right, in undergrad, where they put a slide up and they say, this test is about this one slide, and that slide is F equals MA. They're not wrong, but that instills in you this suspicion, a good suspicion, but when someone says, just look at this slide, everything that you need to know is on the slide, my thought process isn't, I believe that, let me just look at that slide and I'm good to go. My thought process is, oh, you're about to really test deep understanding. So I need to play around with this material on this one slide. I need to play around with it, see how it fits in with each other. And it takes quite a bit of time to realize, wait a minute, a lot of pieces of medicine don't necessarily fit in together yet. And there is no common theme. There is no underlying pathophysiology principles. That being said, there has been major progress in the last 20, 30 years. So I felt like maybe we trained at a really interesting cusp where we were starting to learn these systems-based, in the engineering sense, systems-based principles of how each organ system really interacted. Systems-based, not in the anatomical sense, but systems-based in your body has an exhaust system. Your body has an energy system. Your body has a signaling system. Your body has a control system. Your body has a motor system. And maybe our curricula go through them in an anatomical way, but we were starting to gain basic principles of, no, the immune system is everywhere. It's not just anatomical regions that the immune cells live in, but the immune system comes in and regulates everything. That is a system, just like the cooling system in your car is a system. So it was a weird, I think I paid a price in the preclinical, but the positives of it came back in the PhD, where it was that engineering style thinking, but I had already tried to see the heart, the lungs, the immune system as one system already. So, so just kind of leveraging these different domains to try to understand the guiding underlying principles brought me ultimately to dynamics and control, which I had some foundation in, and took me a while to realize, wait a minute, there's a way to frame everything in that context and put a black box for the principles that we don't necessarily understand. And there's a transfer function there between inputs and outputs that is unknown. So in classic med school learning mode, that's a predictive model, right? I don't know why these inputs are going to these outputs, but I know for that test, I need to explicitly map these inputs to the outputs to get a high accuracy on my test. So yeah, so I think I think I agree a lot with the challenges there. I am curious, and we don't necessarily have to move on, but then third year changes the game, doesn't it?
Well, I want to right, one of the things you brought up, and I like this analogy of where you brought up the idea of regression, or at least let's get broader, machine learning.
Yeah.
And I want to tie that to what you said earlier, which is maybe the engineering way of thinking and this memorization way of thinking are actually opposite of one another.
Yeah.
And I think you have a good point there. Conversation I had with a friend of mine a long time ago, where we were trying to figure out if there's something adaptive about forgetting.
Yes.
Right. And in medical school, you don't want to forget anything, right? And if you forget, you feel weak. You feel like I haven't studied enough. I'm not going to do well enough. I'm not going to look smart enough.
Yeah.
But what you learn in machine learning, and I wonder if you can think of regularization as right. Is this like, in a way, you're trying in some way to forget pieces of data, because what you're trying to do is to essentially see past the noise and figure out what is the true generative model.
Overfitting, yeah. You want to avoid overfitting in your training set so that on the testing set, third year, fourth year of med school, you're able to achieve a decent accuracy versus, but that does come at the cost of accuracy in the training set. Yeah. Regularization was exactly what I was going for. I don't think I finished that thought, but yeah.
Yeah. And so, it is interesting. It's almost, I mean, this is now a testable hypothesis, right?
Agreed. So actually, I encountered this paper early in my PhD, and it completely transformed the way I thought. It was the paper from Aaron Batista, Byron Yu. They're up at Pittsburgh.
Uh-huh.
I think it's called Neural Constraints on Learning. It's 2013, I believe. Sattler et al. Sadtler. It was in Nature, and they did this beautiful experiment. I thought it was a beautiful experiment where they had two non-human primates. They had BCIs in motor cortex. BCIs being brain-computer interfaces for anyone who's potentially watching. These BCIs are little electrodes that go into part of your brain that's associated with movement. It's one of the closest signals to your muscles that tells your muscles to move. So if you're able to listen in on that part of the brain up here in motor cortex and listen in just the right way, you might actually be able to interpret movements and predict what movements the non-human primate, or in some cases the human, wanted to make. So they did this beautiful experiment where they let the BCI learn the combination of electrodes and the combination of weights needed to control a cursor on a 2D screen well. Established work. A lot of really good work from Shenoy Lab out at Stanford. I think Batista did a postdoc with Shenoy. So really solid work. But what they then did was they tested the monkey's ability to relearn in the context of the frame that they already learned. So how they did this was they had 100 channels in their BCI. They learned linear weights between those channels and the ultimate two-dimensional cursor movement. They learned the weights, and then they actually perturbed the weights in two ways. They perturbed them in manifold. So those coefficients, they trace a line in this high-dimensional, 100-dimensional space. They did things like, let's say, just weakened all the weights. All of them, just divided them by 2. The monkey was able to relearn. The monkey was like, okay, I guess within reason, I can make do. I can just double the activity to get to the cursor to where I want. The monkey was able to relearn, and the BCI new coefficients were able to achieve the same performance. But then what they did was they moved it out of manifold. And there's a lot of different directions to move it out of manifold. Their paper goes over how they decided to move it out of manifold in some beautiful way. But when they move it out of manifold, the monkey's performance plummets and stays down. And then when they switch the coefficients back to what the monkey originally learned, it went right back to where it was before. Right back to where it was before. Versus when they did in manifold changes, the performance decreased, they were able to learn again. And then when they changed it back to the old way, it decreased and they were able to learn again. They had this beautiful picture that changed the way I think about learning, maybe in a positive way, maybe in a negative way. But what those coefficient changes could look like is they're adapting to this connections in your neurons, right? Your neurons are connected to neurons in a very specific structure. If you move things in manifold, all you're doing is you're maintaining the correlations in those neurons. You're just weighing them. You're just linearly weighing them with a scalar. If you start going out of manifold, you're now expecting there to be connections between neurons that don't have connections. Two neurons that were firing together now are expected to not fire opposite each other to achieve the same output goal. That doesn't happen in a day. That takes time, if it's even possible. When we learn, when medical school puts a virtue to learning details, what that means is when I hear A, I say B. Right? That means that the part of my brain that does A and the part of my brain that does B, their link is strengthened. It makes it by definition, hypothesis, it by definition makes it so that you cannot do, that network cannot do certain things anymore. And one thing that it cannot do is decouple A and B. Because you learned, like by definition, you learned A becomes B. So when I get asked a question by my attending, I give the answer. So when I'm like, well, what if B but slightly different? That's not a thing that this network can support. But that's the kind of thing we are expected to do in PhD land, in grad school land. What if this isn't the case? Answering, well, I never did that experiment, or it's not in the book, is not a valid answer. So I do strongly believe our brains are networks, and so much lives in the connectivity that when you support one type of learning, you're actively discouraging another type of learning. You can't have a network that quickly goes to its destination and is good at exploring at the same time. Exploring. That's a hypothesis, but it does start, I think, hopefully inspiring questions as to what values should we be prioritizing in medical education when it becomes less about memorizing things within the context of up to date, in the context of clinical decision helpers, and more about navigating and exploring a space to try to find novel solutions.
Let me ask a question, because this, right, the way you're talking about memory is very different than the way that you would ever learn it in medical school.
Yeah.
Right. I don't think this is the kind of language that you know, the folks that teach us would readily use.
Yeah.
So let me kind of ask a very high level question here, which is, you know, there's been a very big push in medicine in trying to enrich the intellectual breadth of the trainees.
Yeah.
Right. And I think, you know, for many years it had been, it would, in order to get into medicine, you had to do biology or biochemistry or any of a number of related fields in order to get in. And, you know, in the last decade, maybe the last 2 decades or so, the push has been very much to try to expand that breadth. But from my perspective, and let me know if I'm wrong, that push has been largely in the realm of the humanities. Right. And I wonder, right, if there would be something to gain if, in addition to that, we made an equally hard push to get people from mathematics, from physics, from engineering, you know, largely because it allows the ability to think about the same problem from a very, very different way.
Yeah.
I'm reminded of this. I just watched a video from Richard Feynman. He did these you know, series of famous interviews on YouTube.
Yeah.
Right, I'm reminded of this example where he's describing seeing a flower, and he's essentially describing some artist or somebody from the humanities that says, "Oh, you know, you scientists, you know, you can't really appreciate the beauty of a flower. You try to deconstruct it." And then he retorts, he's like, "No, I can see exactly what you see. And in addition, right, I can think about the fine scale molecular composition." He's like, "I can think about the fact that the colors in this flower, essentially they evolved in concert with insects, right? They evolved to be attractive for insects. And so now this begs another question, which is there a form of aesthetics that exists in lower order animals that doesn't exist to us, because this thing evolved for other beings, not for us." And you know, all these questions come about because you have an enriched understanding of the world. And so, you know, it's just something that makes me wonder if there's maybe some enrichment that we're missing. You know, partly I wonder if you know, at least in popular culture, folks that are in mathematics, science, engineering, you know, they're a little bit kind of on the edges of what's normal.
Yeah.
Right, slightly ostracized. And
I think so. I think what you're saying is heavily institution dependent. It really depends on what the strengths of the institution are. If the institution has a pretty strong humanities, then they have a few more seats at the committee table, so they might advocate a little bit more for their students. Emory and GeorgiaTech is a very unique situation because GeorgiaTech is there and Emory's there. They're private, public, so there's this interesting interaction. We prioritize, I think, much to the chagrin of some in the MD PhD program, engineers. About my class, about half were engineers. I think since then it's about 3 or 4 every cycle, but it's pretty loose. I think I agree. There's a push to expand the perspectives that come into med school, and I think that can only help. I think it's important to have humanities folks, to have public health folks, to have like music folks. Everyone needs to come in and be given a chance to reframe medicine in their perspective, because we need as many agents exploring the space of solutions as possible. I'm convinced it's all a Monte Carlo, right? Like we're all trying to find that sweet spot, and you need a lot of people. You need to support exploratory minds to go try to find their local minima, and then have them talk to each other to figure out if it's a global minimum. I think it's heavily institution dependent where the priorities are. I think it's good. I think we don't do as much humanities recruiting as we should. In terms of the medical schools as a whole, it might be a lot more. It might be a lot more consistent since it's a lot more top down. There is, I think there is especially recently a bigger push for machine learning style folks, math style folks, engineering style folks. That has been drastically different, just from my perspective, than what I experienced in 2011 when I was interviewing. 2011, I was interviewing. I said I wanted to do statistical signal processing, right? Like I wanted to be a math. I didn't say math, but I said brain signals. I want to do brain signal stuff, and I got a lot of pushback from folks. Like you need to have solid biochemistry, genetics, and I said I'll do my best with that, but it's this math part that's important. I don't see that same level of pushback anymore. I think it's almost the opposite. Let me take a quick 10 seconds if that's okay.
Go for it.
All right. You still there?
Yep.
Cool. Did that address your question? Or
Yeah.
Something you said.
Oh,
sorry.
No, hit me.
Something you said got me thinking. What was it? Oh no. It's funny what getting up and walking around does to your brain state.
Makes the hippocampus do funny things.
Well, maybe that was it. It was this kind of memory. So I naturally, a hammer sees everything as a nail, and at this point I took in my undergrad, I was more of a statistical thermodynamics style person, protein folding, conformational energies, that kind of stuff. Then I switched gears in my kind of post undergrad into more statistical signal processing and that kind of stuff. And dynamics. I took a dynamics course, and that I didn't really appreciate. I loved it. I didn't appreciate how it would come in and help. I just knew it was beautiful. I just knew that these curves were beautiful, that the simple static rules of how flows go could give rise to such rich dynamics on an instance by instance basis. That was just, that was fascinating. And then on top of that, if those rules change over time, you've got a whole other thing that becomes the brain.
So actually, if I could interrupt real quick, because you speak very passionately about dynamics.
Yes.
I think, more than most people. Can you can summarize or try to explain, like, where does this kind of deep-seated love, this feeling that is, it harbors some underlying truth, where does that feeling come from?
Yeah, I think that's a really great point. I think there's two things that give me that passion / confidence. The confidence that drove me in my PhD decision-making and in my projects was very much all the things that we were doing in science regardless are a special instance of a dynamical system. Any system can be framed in the context of a dynamic system. Just make it static. Okay, it's a static system. Make it linear. Okay, it's a linear dynamic system. If it's a linear dynamic and static system, that's the entirety of systems and signals learned in undergrad, right? Input, output, no settling time, all that kind of stuff. So I think one confidence is that I just haven't found something that can't be depicted as a dynamical system. In the beginning of my PhD, I said to myself, accept emotion. Today, I am convinced emotion, just like everything else, can be depicted in the language of dynamics. So that's one. And the other thing is very much, it's the study of change. And that's the one constant across the board. And I say change, not time change, for a very specific reason. Dynamics, by definition, talks about time. How do variables change over time? But a lot of the interest that control theory has is how do your variables change with respect to other variables? So how does the change in your physical state where you are in the US change as a function of whether you're in a car? Right? So x of t, the trajectory you trace out through life, is a function of all these other variables, which sounds like science. So we can reframe science in that context by saying, well, we keep everything constant. So dx by du1, we want to be 0. Dx by du2, we want to be 0. Dx by du3, we want to be the thing we're studying. How does our dependent variable x change with respect to our independent variable u3? And the time part of it becomes the piece that I think was missing in the elegance of answers. That and the best way to convey that is taking a physics without calculus class and learning the kinematics equations, just learning all the how it was structured. There's 4 of them, I believe. Just learning them. It just left me with a funny, weird feeling of like, why these 4? Why these 4? Why not 5? Why not 3? Why are they structured the way they're structured? And then taking a physics with calculus course and change the entire, each of these equations was just a special case of a single equation, depending on what you cared about looking at. So dynamics really seems like the thing that ties things together. It's that unifying principle. It's that drive that I think we all have towards a grand unified theory. We all look to different things to find grand unified theories. We look to physics, we look to faith, we look to purpose, we look to jobs. But I think the shortest way to say all that second point is dynamics is the study of change, and change is unavoidable, but change is also beautiful. We will all change, and trying to resist change just means we're going to change in ways that we're unclear on.
Yeah.
Embracing it, going with the flow, I think it starts getting way too out there, but it's happiness. It's understanding the environment you're in, understanding the limitations of how you can control yourself in those environments, in those dynamics, and then being deliberate in your decision making when it's necessary, and sometimes just going with the flow when it's appropriate. So it really tied together all of my interests, which include neuroscience, but also include non-neuroscience. It includes philosophy. It includes these other things that start getting at the idea of how can you know, and how can you know how things behave when you ignore the fact that they change in time. That's the part that I just can't ever get over. Any model that ignores time has major limitations. So I'm naturally then everything I do starts with dynamics.
I think what's nice, there's kind of a deep theme here that I've been thinking about for a while, which is the power of, it's really the power of mathematics to kind of reveal the beauty that exists out there.
Yeah.
Right. And it's one of the harder things for me to convey in day-to-day life, is that feeling that it gives you. Like, to me, it gives the kind of I get the same kind of chills.
Yes.
Might get seeing a beautiful sunrise. Like you feel like there's something about the world that's just crystallized. Like, I just put something on Twitter today. I think I saw that you liked it or something like that.
Yeah.
Which was, I'm reading a piece right now on information theory, which, it to most people probably sounds like one of the driest things you could possibly read, right? Information theory, yes, no question, bits. Yeah. But what's beautiful about this is that it exists in a very real sense. And so I'll just summarize the passage that I tweeted, which is, right, in information theory, a bit. Right. If I need another bit of information, it is equivalent to saying I need to answer another yes/no question. Right. So bit binary. And so, okay, how can we relate this to something in reality? Right. And so it turns out, if you ask the question of where is a particular molecule of water when it's sitting in ice, you have to ask so many questions. I don't know however many it is. Let's say 10 questions. When that ice melts into water, right, the nature of the change physically is such that I need to ask one more yes, no question, right? It's n plus one question, one more bit.
Yes.
Right? And so the chemists, unbeknownst to this line of reasoning, right, have for years been measuring the entropy changes associated with water melting into ice. And it turns out that if you change the units from what the chemists have been using into bits, you get almost exactly an increase in 1 bit per molecule.
Beautiful.
And like that cannot exist as a coincidence,
yeah.
Right? That reality in some way is it's hard to look at a result like that and not question whether reality in some way is built in these sort of like knowable units.
Yeah.
Right. And that to me is just one example, but there's, examples abound in, I think physics is the most famous field for this.
I think one of the earliest chills I got was pendulum versus planetary motion. I was obsessed with astronomy.
Oh, yeah.
I was obsessed with astronomy growing up, obsessed with Star Wars as well. But I was so into planets, and so it was just this big thing. How could we possibly understand it? And then learning that a pendulum and celestial motion are both this kind of quadratic potential was just like, whoa. This is weird. I didn't at the time know, is this just a coincidence? Is this just the language is able to explain two very distinct things, or there's an underlying symmetry that is manifest in two different ways, through slight iterations, through slight perturbations, the same law, the same rule set, the same dynamic set, just exhibits itself in different ways because you're projecting it in a different light. Which does start. We'll spare the really crappy philosophy that I don't have background-wise, but this notion of a fundamental truth that is seen in multiple ways, or we are all searching for that truth, and everyone's experiences are different. So it got me thinking about the connections between things a lot more, and I think math does this. Math says, what do I need to do to Y to make it look like X? And everything I need to do to Y to make it look like X is information about the structure. How do I make this thing that doesn't look like A? I should not do mixed metaphors or mixed variables. How do I make this Y that does not look like X look like X? Tells me so much about both Y and X. It's that mapping, that morphism from Y to X that contains so much information with respect to certain properties. Am I just looking visually? Well, then I just learned a little something about vision in transforming Y into X. It's this ability to find the connection between disparate things. A, B, C, D, E, F, G are all different letters. What do they all share in common? They're letters, right? Alpha, beta, gamma, delta, those are very different symbols, very different letters, but what do they share in common? Well, they kind of have temporal relationship with A, B, C, D. And I think so I'll stop there. I think there are these cases of shared dynamics, shared laws, shared principles, information theory being a perfect language for that. And then information theory being one central window into the commonalities of seemingly disparate things.
Well, let me lead that into the kind of the big question here, which is how do you take these big ideas, right? That they're abstract, but clearly things you've been working on for a while, and how, if at all, do you try to relate it to the career you have envisioned in medicine? I mean, for you, neurosurgery.
Yeah, absolutely. I think that's a good question. I've been thinking about this a lot recently. I've been thinking about it a lot, but without having a clear idea of what the clinic looked like and what healthcare looked like, I felt a little strange making decisions, but it was a fun exercise. Ultimately, a lot of these, so my PhD background was in deep brain stimulation for depression. This is a classic case of severely ill patients have tried everything else, but really their lives are at risk. Trying an experimental therapy called deep brain stimulation, started in the 70s, 80s, and they get better. They just get better. I know their starting points. Each patient is slightly different. I know their ending point. each point is different, but with respect to whether they're healthy or not, they're all the same, right? Mm-hmm. So how do we trace their trajectories through that space from not well to well? Because those trajectories tell you what DBS does into that state space, in the emotion state space as well as the neural state space, which should have a mapping between the two. So it becomes the language of math, the language of mappings, the language of functions. How do I transform X to look like Y? Well, that's called Y equals F of X. F is what you have to do to X to make it look like Y. What do I need to do in this disease, schizophrenia, to transform it to look like healthy, given the knowledge I just gained from doing that with depression? Finding these unifying principles of DBS, finding out how neuromodulation comes in, affects the neural dynamics, and then how those neural dynamics then get reflected in a change in clinical, emotional, cognitive dynamics. How that fits into neurosurgery is more, I think the neurosurgeons are the engineers of most of these neurotherapies. They're the ones that are on the ground, kind of implanting things. They have the tools, they have a garage, they have to toe the line between knowing things in and out and also adapting to the uncertainties that are always going to be present in the OR. Uh-huh. So the way you do that is by having really solid guiding principles, really solid underlying principles. I can't think of a better word. Principles like, diminished returns. How close do I want to get to this target? Knowing that it takes double the effort to just go slight improvements in that. You need to know when to stop. You need to know when close enough in the brain is close enough without being, irresponsible to the patient. So you're forced to integrate all this information in a way that constantly tests these basic principles that you've developed. And dynamics gives you those basic principles. When I stimulate, I silence two regions. Well, I can translate that into this other circuit. I need to figure out which regions then need to be silenced. Well, then let's go do it. Let's go stimulate there in an OR, do it in a way where you don't have to permanently implant something. You can test it in short term where you won't get long-term dynamic changes, but with a short-term change of this amount, you can predict, hopefully good one day, whether they'll get better 7 months from now. So it's still hazy. I'm still trying to really pack it together in a way that that's not DBS centric. I do want to expand beyond DBS. I think what interests me the most is what neural circuits, what neural dynamics underlie emotion, what neural circuits and dynamics underlie mood. Just to start asking those deep questions about what, all this richness that we see in human interactions, where does it come from? And the neurosurgery part of it is very much just being at that interface of patient care, being that engineer that's working with his hands, and being the scientist slash reverse engineer. I think I'm more of a reverse engineer than I am a scientist. Really figuring out why the thing that just worked, why did it work? Backtrack it, figure out what the black box looks like, and then iteratively improve. So it's all about iteration there. It's not about getting everything in a nice, clean study and really, really, really hammering it through. It's more about that adaptive Bayesian style. I'm coming into this case with this understanding. This last patient changed my understanding this little bit, but I should be careful not to overfit to that one patient. But I can see trends in the last 10 patients. I threw none of that I think was coherent, but those are kind of the pieces I'm playing with as I'm leading up to making a final decision on residency. I'll turn the question right back at you. What how did these pieces come together? We didn't quite get to talk about third year, fourth year as much. That's a whole separate thing. I think you and I both had great experiences in third year where our engineering background maybe set us apart in ways that are hard to even convey, that problem solving part of it. But how do these pieces come together? The medical piece, the engineering piece come together in a decision to pursue psychiatry, I believe.
Yeah. So I'll be applying into psychiatry this year. For me, right, psychiatry, my PhD, just a very quick 1 or 2 sentences of my PhD, it was really trying to understand the kind of the neural circuits and the neural representations kind of short-term memories needed to help guide our second-by-second decision-making. And one of the things that I realized was there's kind of peripherally related to my work are the folks that largely work on humans in the field of cognitive science. Mm-hmm. They typically, I would say cognitive science to me is essentially where mathematics and psychology overlap.
Yes.
Yeah. And what's really beautiful about it, there are people in the field that really take very principled, normative or semi-normative approaches to understanding, various cognitive constructs, why we behave the way we do, how disease arises, things like that. And so what's happened in the last 10 years is essentially a new field has emerged called computational psychiatry. And it means different things to different people. But I think the biggest division in computational psychiatry is you have people on one end of it who care about predictive models. Yeah. Right. This is like primarily what most folks in machine learning kind of work on. And then there are folks that care about generative models, which say, okay, well, what are the underlying principles that allow this system, in this case, the system is the human, to give me the particular set of outputs. And I live more on the generative side because I think it's the domain where we have the ability to get these kind of deep underlying principles, like the kinds I was talking about earlier in information theory and physics. And I'll just give as an example, an area where I think we're still coming to terms with what these advances are, but one of the nice, deeper understandings that I've gotten from this field that I have not gotten from medicine, actually, has been in the study of anxiety.
Yeah.
And so, anxiety, I think we all know what it feels like. We've had moments when we've been anxious. Potentially, these moments have lasted longer than we would have liked. But yet, despite that, I felt in medicine, the kind of definition I was getting was more of an intuitive definition. It's like, oh, anxiety, it's that thing, what it feels like, it's that. Yeah. Whereas what computational psychiatry offered is it said, okay, well, let's just think about the kinds of decisions that people make. As an example, let's just do it through some sort of ideal Bayesian inference agent, just going about the world, gathering data, updating its new priors about the world, and essentially making decisions that way. And using that as a framework, we've slowly realized that one way to think about anxiety is an aberration in uncertainty processing. And in a way, and the data still are a bit messy, but one of my interpretations is a way to think about anxiety is this is essentially it's a disease where uncertainty is just constantly set at a high level, right? And then in that way, if that ends up being a useful way to think about anxiety, it says that feeling of anxiety, that feeling potentially is the normal feeling of uncertainty. Yeah. Right? It's just naturally what you feel. If your brain is saying the world is always uncertain, of course you're always going to feel that.
Yes.
And then once I realized that, an example came to mind, which I said, it makes so much sense for me. When I feel anxiety all of a sudden when I'm driving behind somebody in residential neighborhoods, and I can feel that they're looking for parking. And what that means is that this car is going to all of a sudden hit its brakes. It's going to all of a sudden change lanes. It's going to all of a sudden, switch and turn without signaling, right? And that uncertainty, that lives within me. And I say, oh my God, I'm going to have to be careful because I could get in an accident if I'm not paying attention because of this. And so, that's just one example, but it's one where this kind of top-down approach, this way of saying, okay, what problem is being solved? Yeah. How can it be solved in principle? And what aberrations can arise from this generative process? Yeah. Which allows me to understand. It actually ties in really nicely with what you're describing, because what you're describing is going a level deeper. Right? It's saying I can say, okay, well, the computation we're trying to solve is minimize some uncertainty. You're describing kind of the neural network instantiation of whatever that process might be. How do I get somebody from an anxious state to a not anxious state? Yeah. And so what I would like to do kind of long-term moving forward is to essentially take take these kinds of approaches and apply them to psychiatric diseases generally. And be able to use that for a few things. So the anxiety example I gave, right, one of the things that helps is just understanding. Right, understanding is one of the most powerful things you can have. If you can explain to yourself what a disease is, if you can explain to a patient what they have, it really is a powerful tool. And then all of the other things that can come with that, which is, right, can I diagnose better? Can I prognosticate? Can I tell you something about the trajectory of your disease? Can I tell you how you're going to respond to a particular therapy? So on, so on. Can I come up with new therapies, right? If I understand this black box a bit better, I might be able to think of new inputs that can essentially change the latent variables and push it in a way where, right, you get better trajectories, as it were, kind of healthier trajectories. So, that maybe it's a bit long-winded as well.
No, that made sense. I think the clarity of each piece and how it kind of builds together, I think, is the beautiful part of it. And it's hard to then not see everything in that perspective and want to talk about everything in that perspective. Yeah. This is probably better for a different day and a different conversation, but I do like that model that you kind of high level went over with respect to anxiety as a signal that is typically modulated, and the output then goes to premotor cortex, goes and modulates frontal, I believe. It feeds back into frontal executive function. For a long time, I tried to see what we were doing with depression as a transistor, where you're just broken and the signal that's coming in to modulate your current is just not modulating the current. Your inputs and your outputs are decoupled. And there's this good signal that, and forgive my simple-mindedness, that your amygdala is kind of sending all the time, which is, hey, I be a little bit anxious, be a little bit fearful, be on edge. That typically gets pressed down a little bit through internal circuitry. Hypothesis, and this is a hypothesis. I feel necessary to make this distinction. There's a difference between collecting good, rich data and deriving a model from it that puts so much emphasis on the experiment being very well controlled, very well measured and everything, to derive an understanding from data. My PhD was not like that. My PhD was more like, what are leading thoughts of how this circuit works, project how that should look, what's an alternative approach, what's an alternative model, how would that look, what's an alternative model, how would that look, collect a data set that you can collect, and then do a maximum likelihood estimation, essentially, or most likely, which hypothesis is most likely to have explained the data hypothesis. So I'll say that, and I'll leave it at that. That's a discussion point for hopefully a later day when we talk about inference and controls. But when we do DBS of the SEC white matter, we're hitting uncinate fasciculus, which connects your amygdala to your frontal, right? So it kind of goes backwards through the temporal, goes through the SEC, and goes to your frontal, just distributed to your frontal. And we specifically try to hit that, amongst other things. We also try to hit cingulum bundle. We also hit forceps minor, so there's some hemispheric communication. But the one thing that I consistently saw in our small data set, but rich data set, we had 256 EEG channels in our patients, and when we stimulated the SEC white matter, we saw alpha changes in the temporal channels, the channels right over temporal cortex. I don't know if it's temporal cortex necessarily driving those changes, but I will assume they are for this discussion. And frontal. Yeah,
the assumption coming back.
Huh?
I said the assumption coming back.
Yeah, right? So there you go. You can attack everything. So frontal and temporal, and they did the opposite things. I need to piece together exactly what they did, but one of them was like an alpha, one of them was an alpha decrease, one of them was an alpha increase. And alpha oscillations in the brain are typically associated with synaptic inputs into a region. So increases in alpha are seen in your occipital lobe when you close your eyes. The reasoning, at least the old school reasoning, I'm not up to speed, is with reduced visual input, your occipital lobe is just neutral. It's just kind of an idling car. And when you shift into gear, your engine sounds different. It sounds low initially, could be theta, and then it sounds high. It could be beta, right? So there's an engagement, but your neutral is alpha. What we saw was constantly on the right side. Everything seemed to be on the right side. this right-sided temporal, this right-sided frontal. And the working hypothesis that I came out of that with was very much DBS is such a mindless waveform. It's a 130 hertz square-ish wave that charge balances, and it's just done 130 times. This one waveform, when done in the STN, alleviates Parkinson's. When done in depression, alleviates depression. It can't be the stimulation itself that's introducing information into the network to move its state. It kind of has to be a reduction of a pathological signal. That's the only model that makes sense. That also makes sense in that DBS hasn't worked with Alzheimer's, to my knowledge, and it hasn't worked with some of these more complicated, potentially lack of positive signals diseases. So what you were saying about anxiety kind of just being this on switch and just staying on really jives with at least some preliminary hypotheses of what we saw in our patients in terms of their depression-related anxiety. And also, just to round out the picture, has a very clear dynamical systems language associated with it. There's a critical stable point that patients get into that they're just unable to get out of with standard typical inputs, with comfort, with cakes, with birthday parties. Those inputs come into your nervous system and they don't move you out of that stable point. You're just stuck at that stable point, and that stable point happens to be reflected in your clinical state as sadness, as suicidality, as anhedonia. But it's the key part of it is not so much where that point is, but the fact that that point is stable. And what DBS maybe does is it reduces the depth of that stable point, or it makes that stable point into a limit cycle. It like breaks that single critical point into a orbit that becomes stable. And that's where we all live. We all have cycles in our moods. And when we have an input, we move off that cycle, but we kind of come back to that cycle. That's called a hop bifurcation. I spent a year trying to study hop bifurcations in the math portion, pure math portion of it, and in the control portion of it, in my Europe postdoc, which we can talk about later, obviously. But I just wanted to say that because I think it jives. It jives with this. You tell me. Does that jive? Does that mix? Does that have some resonance with maybe the work that you've seen and done?
Yeah. So, right. So this is where it helps to have formalisms of your problem at kind of different scales. And so ways that people have sort of formalized aspects of depression, right? And one thing, just to be clear, I'm gleaning over many subtypes that certainly exist, right?
Sure.
But a way to potentially think about depression is you might think that part of what your brain does is akin to a reinforcement learning algorithm, where I have a variable called value, right? I have the things in the world have values I've assigned to them. However I've learned them, that's the subject of reinforcement learning. One of the simplest algorithms you can use is when I come in contact with something that I've valued, I'm expecting a certain amount of reward. Right? That's literally what value means. Value is the expected reward, expectation of whatever the distribution.
Yep.
And what happens is I then perceive the amount of reward I actually got from that thing. Right? And so if the reward is more than I expected, now I have a positive prediction error. And then I learn from that. What that means is that my value will increase. It'll move up in that direction a little bit, or it could be a negative reward prediction error. It goes down.
Yeah.
And ways to think about depression within this reinforcement learning framework, and this in particular, I'm describing the simplest model for reinforcement learning.
I like it, yeah.
Is maybe the learning rate is artificially low, right? And the learning rate, what it controls is how much should I learn from this error.
Yeah.
Maybe the learning rate's fine, and your ability to calculate that error is what's disrupted.
Yes.
Right, and there's papers that argue, for or against, a number of these models.
Yeah.
But the net effect of that, right? If I have a system, some neural circuit, and its job is to maintain a representation of value.
Yeah.
Right. If I'm unable to move my value representation around, either because my learning rate is low, either because I can't form reward prediction errors, what that's going to come across is as a fixed point, right? Something that should be moving cannot be perturbed.
Yeah.
right? And the question is now, how do I make it move in a healthy way? And right, and you're describing DBS as yeah.
But in many
and so I would say it totally jives.
Yeah.
Go ahead.
In many respects also, then it critically makes it important to have talk therapy, to have cognitive behavioral therapy. All these things come in and they couple into your dynamics in very different ways. Some of them leverage the structure that's already set up. The structure that's already set up experience the same socioeconomic stressors. They experience the same lifetime developmental stressors. So there's a very valuable, I like it because it's not, DBS is just incidental. It's just a unique opportunity to do targeted control and targeted control in the not mind control sense, but control in the influence sense, control in the medication sense, but then also measurement. But yeah, I think I like I really like that you said that because I have not delved into the reinforcement learning style models for depression, but I'm really glad that that's evolved. And I believe last I looked into it was I believe there was a paper about computational psychiatry in 2016 by GeorgiaTech professor.
That is probably.
I'm trying to remember. I forgot. He came and visited. He was a nice guy. Anyways, I like that I forgot about it and that I can now revisit it. And I'm so excited to see what reinforcement learning models have emerged for depression because I'm a hammer. And there's a great paper from someone up at Berkeley who beautifully reframes reinforcement learning as just modern optimal control theory. Literally the same thing. It's what are your intrinsic dynamics? How do actions change those dynamics? How do those dynamics map to value? Controls is more about continuous spaces, and reinforcement learning for the most part is about discrete spaces, but people are trying to move towards continuous space reinforcement learning. I forget his name, but anyways.
There's a couple people at Virginia Tech. Is Reed Montague is probably the most famous?
Yes, Reed Montague. Yeah.
Okay. Yeah, so he does a lot of like social decision making.
Yes. But he had a 2016 paper about computational psych, and it probably was not the first, but it was the first one that made a splash with my clinical circles, with the neurologists, the psychiatrists. That was the moment we stopped having conversations where I was being told math can't explain depression. Yeah. That's about when those conversations started tapering off and I felt happy.
Yeah, of course.
But yeah, it's I think it's a fascinating field. Time-wise, where are we at?
What am I going to guess? Probably an hour 10 or so.
Yeah. No, this is fantastic. Hopefully we'll get another chance to do this soon. I would imagine.
Hey man, I'm quarantined for another 2 months almost. So.
Me too. I'm quarantined until I take step 2 end of July.
Okay. CK, CS?
CK. CS is a whole thing right now, right?
Oh yeah, see, it'll be online.
You
virtual.
saw that? It'll be 1,300 online. Some Emory folks are really, some Emory med students are very annoyed. I'm hoping.
I mean, the test doesn't need to exist, period.
No.
All right. If everybody passed your test or whatever, okay, let's stick on positive topics. Let's stick on positive topics.
let's stick on positive topics like depression and
understanding. Okay, understanding. That's the thing.
There's so much more we can discuss. I am very eager to get your thoughts about third year, how engineering helped third year, and really talk about. I'd love to have a full discussion about the nature of inference, the nature of influence of management, of therapeutic management, because at least in my experience, and I think your experience, we've talked about this before, is there really is a very clean role for the engineering problem solving approach of balancing understanding with action and iteratively going between those two, and the iteration gives a natural benefit in dynamic systems that change over time, where things that might not make sense in if you just assume the study from 10 years ago still holds. There was an RCT done 10 years ago, but the US's lead level acceptance tolerance changed, then they probably change the results. You need to be able to adaptively improve on that. I'd be curious to get your take on that. So we'll probably save that for a different discussion.
I think, yeah. I actually think that discussion will be really nice because years 3 and 4, I think really tie into that. Because a lot of, I think what an undercurrent of that discussion is going to be the culture of medicine.
Yes.
Right. And years 3 and 4 are that's your first exposure to the culture of medicine. And I think understanding where some of the optimalities and some of the suboptimalities in medical decision making come from. Yeah. So yeah, I think that will be like a really nice intersection.
That'll be absolutely. I think that'll be very exciting. I think it also speaks to a lot of contemporary. Let's be honest. COVID is a very uncertain environment, and being able to be adaptive is crucial. And I think people are having some really good discussions, deep discussions about what constitutes responsible therapy and responsible research. And I imagine our perspectives are at the least different. Maybe not right, but at least different. But yeah, cool, awesome, man. This was a blast.
I agree, man. This is
let's make this. Let's set aside. Maybe let's try this 2 more times, and we'll see if people really resonate with it, like it.
I'm down. Hey, man, I'm down. Package it in my residency application.
Exactly, right?
I'm a heretic. It's heretical.
PsyCom, baby, PsyCom. I'm
reaching out. Two views, you and me. Maybe 3, my mom. All right, I'll add my mom.
Yeah. I am going to try to get some other folks in on this. Of
course.
Some friends of mine, and any friends of yours that you think would really like these types of discussions. One of the beautiful things about, I think, the engineering background is there is such a diversity of engineering backgrounds. Chemical engineers don't talk like electrical engineers, don't talk like biomedical engineers. So how each one comes in, but at the same time, we have math as that unifying language, is a very powerful model for medicine, where CT surgeons need to talk with cardiologists, need to talk with pulmonologists, need to talk with renal folks, but everyone has their own language, everyone has their own lexicon. I think this was actually what I wanted to mention way back at the top of today's session. Language, right? Like, it's important to outline your assumptions, but then we need to be careful about, each of us has a dictionary set. To bring a little bit of signal processing, everyone has a dictionary set. And when we hear words, we project them into our dictionary set, assuming that our dictionary sets match. That when I say I'm efficient when I do this, you and I have the same definition of efficiency, which we probably don't. But we assume we do, and the rest of our conversation moves forward with that assumption. Same kind of thing, like, how do we get a unified language amongst medical professions, specialties, especially us in a unique situation where we got to see all of them over the course of a year. I'd be eager to sort of talk about that. It's a little bit of a teaser if anyone is actually watching this. Cool. But yeah, anything else?
I think that's it.
Good stuff,
this has been a rejuvenating post-run conversation.
For me, it's pre-run, but it's good too.
yeah, of course.
Be good things to chew on while I'm running.
Yes. Yeah.
All right. Thank you very much, Bilal.
Peace, my friend. Right. It's good. Not a doctor until you're a doctor.
That's true.
All right.
I'll catch you later.
All right. Take care.
See you. Thanks for joining, everybody. So we'll try to do this more often if people are interested, but honestly, it's a lot of fun to talk about these things, to kind of work through a lot of these experiences that we've had in the long MD PhD path. Maybe we'll get some more professional stuff set up, maybe not. We'll have fun with it. Hope all of y'all are staying safe and, keep at it.